And so this is a talk about chiral, it's a talk about Weyl semimetals. I looked at the program, I have the impression it's the first Weyl talk of this week, pretty much, right? There'll be more after this, so I thought it might not be bad to give some sort of introduction, a little bit on this new topic in condensed matter physics. So I'll give a bit of an overview of what it is, and then I'll tell you some of this stuff which is very close to my mind, and which I think is lots of fun. So this is things which we published in the Journal of Physics earlier this year. With Paul Bayreuther, Jimmy Huttershoek, and Jakob Trujillo. And I've continued working on this, and some of the people whom I'm working on it are actually here. Tom O'Brien will give a talk on his most recent stuff, I guess tomorrow. So I think it's a very beautiful new topic in condensed matter physics, and I think there's lots of fun to be done. That's probably what I want to convey to you today. So this was one of the key discoveries of 2015. Discovery of a Weyl semimetal. Not just one, but a whole bunch of materials which had this unusual property. And after 85 years search, I'm not sure that it was an 85-year search that refers to Mr. Weyl, but he would be very surprised, I think, to see what we've called after his name. But still, it's something which theorists have been thinking about for many decades, and now it turns out actually that there's lots of materials which have this unusual type of quasi-particles. And this is just a list of early experimental groups, but the list is much longer now. It's actually a very broad area of material science. It's kind of easy. It's not like topological insulators, which is much harder. So there are many groups who are working on this. It's really exploding experimentally. I think that's part of the reason why it's considered such a healthy field. Many experiments. Theorists also. Many experiments. Okay, so yes, it completes the trio of elementary fermions, the usual electrons, which the Dirac fermion, then there's the Majorana fermion, which may or may not have been observed. We've had some talks here, and maybe some more talks on that. And now we have the Weyl fermion. So somehow this completes at least the three individuals who have named a fermion after them. I don't think there's another person who has a fermion after his name. So that's kind of satisfactory. But let's see what it's about. So if you're talking to someone and he says, my topic is Weyl semimetals, and then most often these people will then say, it's just three-dimensional graphene. But the idea being that many of us know about graphene, many of us have been exposed to graphene, and the quickest one-sentence way to tell you what I'm working on is to say it's three-dimensional graphene. Graphene is a thin sheet of carbon atoms with massless electrons, and now they move in 3 dimensions. Okay, that's good. It's fun. It's actually also poisonous graphene. Graphene is good because it's very inert and healthy, and you don't have to worry about it. But all these materials, all these 3-dimensional versions of graphene are poisonous, dangerous materials. So that's not so good, but probably you've exhausted the things you could do in 2D, and then you move to 3D. But this actually does not do justice to the field. It does not do justice to the field. It's much richer than just 3-dimensional graphene. So let me try and walk you through this. By the way, if you want to interrupt me during the talk with questions, do that. It will be much more lively. You see people coming in, and everyone sleeping, and the fan is whirring. So it's a bit of a distracting environment. But if you want to ask questions, I'm sure it will make it much more lively and enjoyable. Certainly for me. So go ahead. If you have a question, just reach out. Okay, so, graphene, I don't need to explain graphene, I imagine. It's the Dirac, the 2-dimensional Dirac Hamiltonian. The Pauli matrices, sigma x, sigma y. There are just 2 Pauli matrices because we live in a plane. There's px sigma x, there's py sigma y. But then you have a 3rd Pauli matrix, and you can add it. Of course, you cannot add it with pz because there's no pz. So we added with this thing which we call mu, which is like a mass. And so this Hamiltonian here describes massive Dirac fermions. Unfortunately, in graphene, this mu is very small. But if you put graphene on a substrate, you can have a non-zero mu, and then you can open a gap. And in fact, people like to do that because to have a material, a semiconductor, which is gapless, is very inconvenient. It's much more convenient to have a gap. You can do all kinds of electronic and optical experiments with that. So this mu term is kind of important, and this will open a gap. Here, the Dirac cones will split. So now we're in 3D. In 3D, in first instance, what we do is just add a PZ, right? So we just add a PZ sigma Z. And then we can still have our mass term. But now you see this mass term doesn't do anything anymore. Because it's just a displacement of your coordinate of momentum, right? So this PZ plus mu, we call it the new momentum. And so the mass term has become irrelevant. And this is unique, and that's the fun thing of going to 3 dimensions. The reason for going to 3 dimensions is not because you want to write more papers and you've written all the 2D papers you could write. It's because in 3D, the massless feature is protected. That's the jargon of the field. It's protected, topologically protected, perhaps even. There is a way in which it's topologically protected, but basically it's protected because we've exhausted the Pauli matrices. So only 3 Pauli matrices, and so this is it. There's no way to gap this cone. There is actually a way to gap the cone, but it's a dramatic, destructive way. The cones always come in pairs. It's also like this in graphene. Right? In graphene, there are 2 inequivalent Dirac fermions, the 2 corners of the opposite corners of the Brillouin zone. And here it's the same. There's never just one Dirac cone. There's always another Dirac cone. They don't, unlike in graphene, it's very much symmetry based. That's why graphene, there's only one graphene. And why aren't there dozens of graphenes? Because there's only one graphene. It's very much tied to this honeycomb lattice. But in 3 dimensions, it's not tied to symmetry. That's why there are many materials. And so there's no such thing that these cones sit at special points in the Brillouin zone. They can be anywhere in the Brillouin zone. In fact, there can be more than 2. But 2 is the minimal number. You cannot go less than 2. And the way you destroy them is by bringing them together. If you bring 2 of them together, then the gap opens. This actually also tells you why you cannot have less than 2, because death and birth are tied together, right? And so if the only way to kill them is to bring them together, it also means that the only way in which they can be born is if they merged. So these things are intimately tied together, and that's why you always have an even number of them. But 2 is the smallest number. I should say, in all fairness, that at this very moment, we do not have a material with only 2 Dirac cones, with only 2 Weyl cones. There are materials with 4 Weyl cones, so we're getting there. We started with, I think, something like 24, huge number, but this has been brought down, and the smallest number is 4. So we're on our way. As a theorist, I prefer to just work with 2 Dirac cones. Life is complicated enough, and then let the material scientists catch up. Okay, so that's the story of the protection, but there's more to it. This is just one thing, and so this is the jargon of the field, topological protection. There's another thing which we know about Weyl fermions. Of course, Mr. Weyl, Hermann Weyl, I think, he thought of these particles as elementary particles, and his Weyl fermion was a massless fermion. And these two types of fermions, here we have 2 types of them. In that jargon, they're called flavors, left-handed and right-handed, left-handed and right-handed Weyl fermions. And so there's a certain sense in which they have a chirality. Left-handedness and right-handedness means something about spin and direction of motion. And it's the same actually in the solid state. So also in the solid state, these two different Weyl fermions have a different chirality. And the easiest way to see this is, there are 2 ways to see this. I'll come to the other way in just a moment. But one way to see this is that somehow these these chiralities, they're connected at the surface. This is something which is kind of special. I like to think of it in this way. Topological insulators, they have a boring bulk. But the bulk of a topological insulator should be boring. It's not, then it's not a good topological insulator. But the surface is very interesting. The surface is conducting, so that's fun. Now in a Weyl semimetal, the bulk is interesting. There's this Weyl cone, which is fun. You could imagine doing fun experiments with that. But also the surface is interesting. So they really have combined the best of both worlds. Because what happens at the surface is this. So we typically do not use chirality here. We may use chirality, but typically we call Berry curvature, which is another more advanced theoretical concept by which we can distinguish the two types of Weyl fermions. So this Weyl point here has this notion of Berry curvature, sometimes called a Berry monopole. And there's a state which connects Weyl points of opposite Berry curvature. Here's the state, and the state is on the surface. So in the bulk I can just have the two Weyl cones. I mean, I just wrote my Hamiltonian with one Weyl cone. Nobody said that there should be states connecting to it. But once you try to terminate the crystal, then you find that you cannot sustain this. Then you find that there will always be states which go from one Weyl cone to the other Weyl cone. And these states, they form an arc. Typically surface states are like a circle, a Fermi circle. If you look at all the states at one energy, you get a circle or an ellipse. But here they start and they stop. It's kind of unusual. You cannot do this in free space, right? I mean, in free space, the Fermi surface should always be closed. It can't just stop. But here it can stop because it's not in free space, it's at the surface. So stopping just means that, yes, the state stops. It means that it enters into the bulk. So what happens is as you follow this line here, as you approach these points here, you find that the state is less and less bound to the surface. It's less and less bound to the surface. And when you hit this point, it's totally unbound and just disappears in the bulk. So there's nothing unusual. It is unusual, but it's not paradoxical. And so these are called Fermi arcs.
Can you actually go through that point? Because the state should be orthogonal. It's about saying the surface state.
Well, no, I think you just evolve. There's a very natural, if you plot the dispersion relation, I'll show you the dispersion relations in just a moment. They're orthogonal in the sense that typically if you write a dispersion relation, there's a conserved momentum, and different momenta are orthogonal. But if you have some way to drive the momentum, for example, by applying a magnetic field, this is actually an experiment which has been done, beautiful experiment, spectral flow, where you apply a magnetic field and drive electrons from this Weyl point to this Weyl point in the bulk. Beautiful experiment. You see it in Das von Alpha fellowship of the Haas oscillation. So yes, you can actually drive your particles from one Weyl point to the other by a magnetic field. Okay. So now something more about the chirality. Yet this whole word chiral is still a bit in the air. So let me tell you how you can see the chirality, even without looking at the surface. So this is something which was done in the very early days, long before these experimental discoveries. People asked the question, what happens if we apply a magnetic field? Don't worry about surfaces now, just give me the bulk. Just give me px sigma x plus py sigma y plus pz sigma z, and I'm going to add a magnetic field. You know, the usual way, you add your vector potential, and you solve for it. Now you may remember in graphene, this gives very interesting results. In fact, the key, I still remember this very vividly, the first experiments in graphene did not really attract the attention, certainly not the attention of theorists. You know, somebody says that they've made a single layer of carbon. I remember people coming up to me in conferences saying, hey, this may be interesting. I said, well, perhaps. The experiment which caught the attention of theorists was the half-integer quantum Hall effect. When Gaiman and Weyl and Philip Kim found that in graphene, the quantum Hall effect doesn't go n plus 1/2, but it's 1/2 times n. So you start from 0, and then you move with steps which are 0, 2, 6, 10 instead of 2, 6, 8. So this is a strange effect in graphene. Strange effect in graphene. The 1/2 is missing. Sometimes it's said that in graphene the 0-point motion is killed, which is true. The 0-point motion is killed by the Berry phase. So it's somehow a fun thing. Now here's something way more dramatic happens. way more dramatic than this counting. Should I start from 0? Should I start from 1/2? Which is some sort of a detail. Something way more dramatic happens. So we're in 3D. So really 3D, motion parallel to the field is not influenced, right? You have a field, you can just move parallel to the field. And so Landau levels are not flat. They will always have a dispersion in the direction of the magnetic field, so they're parabolas. So Landau levels are in 3D are parabolas. Here's one of these Landau parabolas. Another one, another one, another one. This is the P3 here, this is from Zoll paper. I didn't send it here. So this P3 is momentum parallel to the magnetic field. Here are the parabolas. Now what about, in graphene we had a 0th Landau level, which was kind of special. What about the 0th Landau level here? Yes, it exists. It moves parallel to the field, and it only moves in one direction. It cannot move in the opposite direction. This is kind of bizarre. It's bizarre if nobody told you that there were 2 types of fermions, right? If people said, let's just look at this Hamiltonian, dx sigma x plus by sigma y is z sigma z, and all of a sudden you find yourself with a particle which can only move in one direction. Well, that's going to give lots of troubles, right? I mean, where did they go to? I mean, where did they come from? So this already tells you that they must come in pairs. There must be another particle which moves in the other direction. Of course it does. The particle with the opposite chirality, which does like this. So there's no paradox here, but if you just look at one Weyl cone, it appears as a paradox, and this paradox is called anomaly. And this is called the Chiral anomaly. And it comes if you don't look at surfaces, you don't look at, you just look at one Weyl cone and you think this is bizarre, it doesn't make sense. Okay. And these people in actually a solid state application, I imagine they were particle physicists, but they thought of a solid state application, condensed matter application, imagined what would happen if you would somehow, they were aware of course of the fact that you have these two Weyl cones, but what if you create a population imbalance between them by this thing which is chiral chemical potential? And only a theorist could invent this word, right? Because you cannot go to a lab and say, please apply the chiral chemical potential, but as a theorist you might invent it and say, okay, what happens if I have more electrons of this type than the other type, then a current will start to flow. So a current will flow parallel to the magnetic field, driven by this chiral chemical potential. And one could ask, let's calculate this current. Can we calculate the current? Well, it's very easy to calculate the current because this is just it's just one mode, one multi-degenerate mode. And so the current is just, what is it, E squared over H, right? The current by one mode is E squared over H times voltage. The voltage is mu. And now then you have to find the degeneracy. The degeneracy is number of flux quanta through an area. And you just plug in the numbers and you find the current density, which is E over H squared times mu. It drives it times B. B gives you the degeneracy. So it's quantized. You have quantized the current density. Beautiful effects, fundamental effects. Amazing. Let me just check for one brief moment. Did I actually start exactly at 9 sharp, or did I start later? 9:02. Very good. Sorry, I had 40 minutes, right? That's great. Okay. Okay. So this is fun. This is beautiful. And if only we had a chiral chemical potential, and we don't. And so there are you can find on the internet experiments saying we've seen the chiral anomaly, but it's always indirect. There's always a storyline. We say we see this effect, this magnetoresistance effect, which we can only explain in terms of the chiral anomaly. It would be much more fun to just do this, right? But we cannot do it. So now comes basically this is where we started, and now I show you band structure. This is a band structure, energy versus momentum, and I find it convenient always to work with a finite system because if I don't have a finite system, things can be really you can fool yourself. So in the finite system, I have a cylinder. Here's a cylinder, parallel to the magnetic field. There's actually no magnetic field in this situation here. This is zero magnetic field. Here you see the two Weyl cones. You see the two Weyl cones are displaced along the momentum axis, and I've also displaced them along the energy axis. This is not applying chiral chemical potential. This is just something which is built into the material. It's strain. This is what strain does. So strain displaces them in this direction, and the magnetization displaces them like this. So we have these two handles, we have beta and mu. They're not tunable handles. A given material has a given beta and a given mu. It's still, it's useful to have a situation where you're displaced like this. So now that this Fermi arc, which goes from one Weyl point to the other Weyl point, has a dispersion. It disperses, meaning its energy depends on momentum, which means that there's a velocity associated with them. So these surface states, they spiral. That's kind of neat. So if you have a wire, I call it the Weyl solenoid. It's not particularly, unexpected, but somehow I don't think anyone noticed this, and it will be absolutely crucial for this carbon effect. So you have a wire, a solenoid, parallel to the, there's no magnetic field yet. I'll apply a magnetic field in a moment. You have this wire, and it has a current winding along its surface, as if you were given a solenoid. And of course, the solenoid, you didn't make the solenoid. Nature made the solenoid. So here are these states which spiral along the surface.
Is there anything deeper in the fact that this looks exactly like the dispersion of a zigzag nanoribbon?
Well, first of all, the dispersion of a zigzag nanoribbon, this would be flat.
Not really.
Because of next nearest neighbor hopping, yes. No, there is a similarity between zigzag and this. It's only that here it's topologically protected, and in graphene it's not. So many of these effects, you could imagine doing them in graphene, but they would not be topologically protected. You could, in fact, the edge state, the zigzag, you can get rid of it. It depends on the details of the... So there's similarities, but it's much more fun because it all follows from topology. I didn't have to give Hamiltonian, I didn't mean to tell you what the lattice symmetry was. It just follows from topology. Okay, now comes basically, I'm already doing very well with my time, and I'm only starting after the introduction, but it's good, because actually what I have to tell you, I can tell you already in this slide. Here it is. So I look at this state, I say, it only moves in one direction. Isn't this some sort of Carlo anomaly? Well, it's certainly not the Carlo anomaly of Nielsen and Ninoyima. I mean, there's no magnetic field yet. But if I only looked at the central portion of the Brillouin zone, I would see states moving only in one direction. Of course, there's no mystery here. What will happen with these states is that they will reconnect here in the bulk. And so these states which only move in one direction have counterflow in the bulk. But if I only look at the surface, I only see stuff moving in one direction. So I could have a Carlo anomaly here, why not? So how would I drive this Carlo anomaly? Now comes the fun thing. In the Nielsen-Ninoyima thing, you had to drive it with this Carlo chemical potential, which doesn't really exist. Here I can drive it with a magnetic field. How do I drive it with a magnetic field? Well, I want to populate these states. Right? Let's say in equilibrium, the Fermi level is like here, every left mover is balanced by a right mover. No current. This is not a superconductor, no current. I want to drive it out of equilibrium and get a current. How do I do that? Well, I have to populate these states. How do you populate them? By pulling them down. Pull them down and then create electrons or holes. How do you pull them down? Well, I give you a solenoid. How do you pull states down in a solenoid? Just apply a weak magnetic field. Right? State has an orbital angular momentum, it has a magnetic moment, magnetic field, so pull it down and push it up. And in fact, you can immediately calculate what this current will be, because the magnetic moment of this thing is just the velocity times the enclosed area, the current times the enclosed area, and so you just fill in the various numbers, and you immediately get the dJ dB, so the current induced by a magnetic field at fixed mu. I mean, this is in the Nielsen-Ninoyima effect, the magnetic field was fixed and large, and mu was varied. Here, mu is fixed and large, and B is varied. So it's dJ dB, but it's the same number, E over h squared times mu. It's the same effect, but now it's zero magnetic field. Well, zero magnetic field, meaning I need a magnetic field to drive it, but it's an infinitesimal magnetic field. I can take the limit of B to zero here. No Landau levels. This is completely unrelated to Landau levels. This is not Landau. It's a different effect. So that's fine. Good. So I'm actually almost through the time which I have for my talk, not quite. But that's good, because all the rest is just the usual thing we do as theoretical physicists, you cannot really, I mean, this is great for a talk, but you cannot really imagine writing a paper like this, right? Now you have to have calculations, working on yourself. So that's what we do, and that's what we did. So let me just, I call this the Carlo anomaly without Landau levels. Hey, there was just a Nobel Prize last week, right? For the quantum Hall effect without Landau levels. So it's good, right? This is good stuff. So this is a slide which I'm just going to skip, but if you're asking what have we been doing since we did this, we are coating it with a superconductor, and there's lots of fun stuff I can tell you about that. But I'm going to skip it, you can read it. So now we have this thing which we call the Weyl Majorana solenoid, which is also absolutely awesome and amazing. But I thought for this conference, this is my introductory talk. With that, I'm going to skip this. Yeah, I do want to show you this thing, because there are many theorists here. And so how do you do this theoretically? I mean, how do you do stuff? Well, I'm old in this business, but not that old. So if you would be really, really old, you would say, okay, let's apply the Kubo formalism, right? That's how we do transfer properties and condensation. Let's do Kubo formula. Okay, I'm not that old. I'm let's say, from the 1980s, and since the 1980s, we know that Kubo is not so convenient, particularly if you have surfaces. Landauer is much more fun. It's much better, much more convenient. And so I want to do Landauer for the chiral magnetic effect. Now there exists a Kubo formalism for the chiral magnetic effect. It exists, and I think actually Dima Pizin will tell you about that. I think even today or tomorrow. But this is awful. I don't want to do Kubo. I want to do Landauer, and so I want a Landauer formula for the chiral magnetic effect. So it will be like a Landauer formula, where instead of driving it with an ordinary chemical potential, you drive it with a chiral chemical potential. Well, you can do that. Here's the idea. So this is again this dispersion relation, and you know what we do with Landauer. We look at modes at the Fermi level. Right? So we draw a line. We say this is the Fermi level, and we look at all the crossings, and these are called modes. And we look at modes which move to the right. They have a slope like this, and we have modes which move to the left, they have an opposite slope. And then we ask for the transmission probability of that mode. That's the Landauer formula. It says, give me all the modes, give me the transmission probability. Conductance is sum over all the modes weighted with the transmission probability. Same here. The current is sum over all the modes weighted by the transmission probability. Here I put, in the usual Landauer formula, you would drive it by voltage. Here I could drive it with this chiral chemical potential, but that's not what I want to do. I'm going to drive it with magnetic field, so I have a delta V here. And I do have a different weight factor here. In the Landauer formula, the weight factor is the derivative of the energy with respect to the voltage. It's just asking, if I apply a voltage of 1 electron volt, how much of the energy of the electron changes? Well, of course, if you apply a voltage of 1 electron volt, the energy of the electron changes by 1 electron volt. Right? But here it's different. Here I'm asking, if I apply a magnetic field, let's say of 1 Gauss, how much does the energy change? So we have there's a magnetic moment here. This is different for every mode. So this number here is mode specific. It's the magnetic moment of that mode. It tells you if you apply a magnetic field, how much does its energy change. So it's dEdB. And you also have to weigh with the sign. Somehow in the Landauer formula you can get away with that, but here you have to consider both left movers and right movers. It's because in the Landauer formula you apply the voltage from going from the left. So you can say the right is at ground, it's grounded, so you only have to look at left movers. But here, I cannot do it. Magnetic fields everywhere, so I have to weigh with the sign of the dEdB. So here it is. This is the new Landauer formula for the chiral magnetic effect. I'm sure Rolf Landauer would love it. Many of us want to buy it.
Is it possible to see this delta B as a window in which I count the levels?
No, the window is the temperature. Delta B is I'm not prepared yet to do nonlinear transport here. So I've linearized everything. So this is different. In the energy window is still temperature. So here there's no temperature because I've taken the limit temperature to 0. I have a more general formula where you actually have to integrate over an energy window weighted by derivative of Fermi function. So temperature still gives you the energy window, magnetic field will not give you the energy window. So the answer is no. This does not carry.
What is delta B?
Delta B is my, okay, I start from a system in equilibrium. I'm going to drive a current. How do I drive it? Well, I drive it by applying a weak magnetic field. Now, of course, if you apply a weak magnetic field, after a while the things will equilibrate. So there's weak magnetic field that oscillates slowly, which is indeed is what, I mean, this is not something which I invented. This is what it's supposed to be doing. So you slowly oscillate in the magnetic field, so that you on time scale smaller than inelastic relaxation times. So delta B is a driving force. Yes, please.
So, how is the device made? Are you having this wild?
Okay, let me go now because I see my time is now running out, which is perfectly okay. So I will take many more questions, but yes.
So, do you have relaxation as you turn on your magnetic field? and energy levels move. So you have relaxation.
Yes. Okay. So this is in the spirit of the Landauer approach. Inelastic scattering is not included. So I'm assuming that the whole thing, the time scale of this oscillating in the field, that elastic scattering is fully included in the T, but inelastic scattering is not included, and I would not have an easy way to include it. This is probably a drawback of the whole Landauer approach. We have all these voltage probe things, but inelastic scattering is not easily included.
But then you do not change your distribution function.
Of course you do. Of course you're pulling stuff down?
No, yes, energy level moves.
Look, my friend, oh my goodness, you know, if I suppose this thing has a magnetic moment, okay?
Right.
So I apply this magnetic field. Right. You can be absolutely certain an electron which was first here will then be here.
That's right, the energy level moves, but the incubation cannot change.
No, this is right. So I've created, exactly, that's why you've created either a particle excitation or a whole excitation.
No, so you're...
Okay, this is a discussion, we'll have to do this at coffee, I'm sorry.
You're not changing, your velocity does not change.
No.
Your distribution
Okay.
does not change.
I really want to discuss this with you, but this is, I cannot do it at this moment. Right? So if you allow me, we'll sort this out, don't worry. Okay. So in fact, just to show, okay, what can I show you? So this is Hamiltonian, I'm going to show you Hamiltonian. This is numerics, which we did. The line here is the prediction from the Landauer formula. The dots are a computer simulation. We actually also checked with the Kuba formula. So Paul Bayreuther, who's the hero of this thing, spent 1 full year doing this calculation with the Kuba formula. And this takes half an hour. Yes, it gives the same number, so this is this universal number. There's a bulk contribution, which is interesting. The bulk contribution is interesting. When we put this thing on the archive, I got an email from Burkov, who's one of the heroes of this field. He said, I'm very happy that you calculated surface and bulk. I was always concerned that I've only looked at the bulk, that the surface would cancel it. And there's reason to be concerned, because yes, the surface does cancel it, but only by a factor of 2. So the bulk contributions are minus 1/2 the surface contributions. And that's good. I'm pretty certain about this factor of 2. Of course, this is something to be slightly frightened about. Perhaps we lost a factor of 2 somewhere. The whole effect's gone, right? So I have a whole bunch of different ways to calculate this minus 1/2, numerically, analytically. I'm pretty certain about it. But I do not have a first principles way to get this 1/2. And that's unfortunate. And I hope someone will be able to do it. I wish that there was just a first principle way to know that it's minus 1/2. I do not. Please.
I think it's actually the other way around. Bulk is twice the surface.
Look, my friends, I think, okay, look, with my group, we've been working on this for perhaps 1.5 years. You listen to the talk, and you somehow want to imply that all these numbers are just bogus and wrong. I'm quite willing to address these things, but please, some degree of trust that, yes, when I say 1/2, that it is 1/2, not 2. I'm absolutely convinced that it's minus 1/2.
The story goes back 40 years. And
Okay,
we have here when people talk about polar short gravity.
Can we finish the talk and then continue this kind of discussion?
We put this on the archive, this thing will hopefully be published, so I'm putting my neck out and saying it's minus 1/2. If someone stands up and writes a paper and say it's actually minus 1, which would be even more dramatic, but even a plus 2 or minus 2, I've lots of stuff at stake here. The calculations are there, you can read them, so I'm not just bragging about something which I cannot justify. I'm absolutely convinced that it's minus 1/2, but I'm willing to entertain criticism, in particular if it's backed up by a calculation. Good. Okay, we also did the original effect. This is also a very convenient way to study the original Carlo magnetic effect, the ones by Nielsen, Inoyama. In fact, it's a very convenient way to find surface effects. So here the effect is completely due to the surface. It's entirely a surface effect. But in the original Nielsen-Inoyama thing, it's a bulk effect, but there's surface corrections. And this is a plot of surface corrections. You see, they're pretty big, actually. We have also an analytical theory for this. So it's Landauer formula, since it starts from a finite system, it's a fantastic way to deal with finite size effects. I don't think anyone ever did finite size effects on the Carlo magnetic effect. So you can see the finite size effects. Different widths. Eventually it will level off at the established value, but it's very slow convergence. Good. Okay, the final thing, which I think also Jaroslav's talk. So what is the experiment I might have in mind? Well, I don't really have anything, but here is a biosemimetal. It's a cylinder. Now, you could drive it with an oscillating magnetic field and then measure an oscillating current. Probably it will be easier to do the inverse. We don't really have sources of microwave sources of magnetic fields. You could drive it with an oscillating current and measure the induced magnetic fields. Of course, if I tell you that the thing is a solenoid, you'd say, well, I know about solenoids. I know how currents induce magnetic fields in solenoids, and this, of course, trivializes it, which is okay. It's just that this solenoid happens to be topologically generated, so I think it's, even though it's just a solenoid, it's a topologically generated solenoid, so I think it's kind of fun. Good. Surface effect, bulk effect. I have one final thing, and then I shut up, and we even have a couple of minutes for talks and for questions, I think. So we just had last week at least some share of the Nobel Prize for the quantum Hall effect without magnetic fields, which is called, does anyone know how it's called, the quantum Hall effect without magnetic fields? How is it called? Has a name. Quantum anomalous Hall effect. Not anomalous quantum Hall effect, it's something else. Quantum anomalous Hall effect. So here I have the chiral anomaly without a magnetic field, which is called the chiral anomalous anomaly. Thank you.
Okay. 2-3 questions. Please remember, if you have criticism, it cannot be hand-waving. It has to be backed up by calculation. So if you want to criticize, you say, I have an archive 160.
No, but it's okay. I don't want to. I was too harsh.
No, it's really
I was too harsh. I apologize.
No, it's okay.
I'm just managing time. So
No, but
time.
I was too harsh. I apologize. I should not have been.
That's all right, really. It's all right. Physics is not polite. That's fine. So, could you predict the amount of current that will flow on the surface in a time reversal invariant?
Then it's gone. Then it's the whole thing. If there's time reversal, no, obviously. I mean, it's solid. How does it know in which direction to spiral? It's because time reversal symmetry is broken. So if I would have preserved time reversal symmetry, there's nothing. No solenoid, no nothing.
Well, of course, there's source of current in that case, and it's just right in order not to have polar Kerr effects. So baking this up goes back to Onzager, which basically tells you that's the case, right? So that's the point. One half. The other one half the other way, comes from Onzager relations, right? Which guarantee that there is no polar Kerr effect in time reversal invariant system.
I would love to have an intuitive, understandable argument for the management. I've talked about this to many people. I have a colleague, Vadim Chayanov, some of you know him because he's a relative visitor here. He says, I can do it. And you know, it's 6 months later and it has not happened. So I would love to have, I mean, someone has a theory. Here, I'm going to offer you something. I'm an editor of New Journal of Physics, my favorite journal. If someone has a theory, a quality theory for the mind,
it's impossible. It was
send it
published
to
40 years
NJP
ago.
and you'll get premier treatment, I promise you.
40 years ago it was published. It's a paper by Yudson and Agranovich. Okay, I guess that's it. It's really not.
Other questions?
In this device, which is on the slide, do we need the alternative B to drive the current, or actually if I put constant B?
No. So there's no miracle here. It's not a superconductor. What happens if you apply a magnetic field is you'll initially generate a non-equilibrium population, which will just relax. You have, if you look at one energy, you'll find some states are filled, some states are empty, and so they'll redistribute, and so every left movement will be cancelled by a right movement. So there's no, this was an initial confusion which has now been settled. Marcel Franz has a PRL on this. It was a bit silly that we still have this confusion these days, but no, in equilibrium, all states are filled up to one energy. Every left mover is balanced by a right mover, surface is balanced by bulk, and so there's no current. So, no.
But how is that reflected in the picture of scattering amplitudes and is that somehow related back to the question of occupations, or?
Well, it says that I'm driving. What I do is I start from an equilibrium situation. I apply some perturbation to the system, and I ask what's the adiabatic change in the in the distribution function. I just transform the distribution from adiabatically, then I get a non-zero current. But of course, we know that this will not be sustained, because at a given energy we'll have coexisting filled and empty states, and so they will just scatter and relax. And so this adiabatic change in the distribution function cannot be sustained.
So is this related then to like pumping? Because in pumping we don't apply chemical potential.
It's non-equilibrium effect. There are many ways to drive a system out of equilibrium. And the magnetic field is just as good as any other one. And at least that's what I hope.
But in pumping we apply time-dependent potential and then we get current flowing. So
I would imagine in pumping, you're moving from one equilibrium state to another, aren't you? You're not. You're driving a system out of equilibrium. It's a linear response. You can do this with Kubo formula. In fact, we did it with Kubo formula. So it's just, in that sense, it's a conventional linear response theory for a system out of equilibrium without inelastic scattering. Not including with elastic scattering. We're hoping that the time scale for elastic scattering is sufficiently long that it can work.
So if I understand correctly, you need to start with something which is ferromagnetic. You said it has to have a broken time reversal symmetry.
Yes, and
so it must be somehow ferromagnetic.
Yeah.
And you also, of course, want it to be a hard ferromagnet so that when you apply your current. Or
yeah, I'm not sure that it's ferromagnetism. I think it's some exchange. So these Weyl semimetals come with an intrinsic broken sign of time versus symmetry. It's probably some exchange effect, which pulls the Weyl points apart. It's not necessary to do this, but
so there obviously have to be two different phases. If you have broken time reversal symmetry, you have another state which has exactly the same energy. If you're not applying a magnetic field, you have to have two different crystal forms or something that have. One has,
yes.
Usually that.
And there I must confess my ignorance. I just look at the materials which people give me. I mean, just on the internet, and there's a whole bunch of all these Arcus experiments which find Weyl points which are displaced along the momentum axis. And so
the energy axis that we're concerned with.
No. The displacement along the energy axis is straight. That's inversion symmetry breaking. It's the displacement along the momentum axis. A magnetic field is like a vector potential. So it's so here I had the slide which I thought had this. Okay, here we are. Actually, this is the Hamiltonian. There's the term beta sigma z, which is the one which breaks time versus symmetry, and beta can be seen here. Beta is the displacement in the momentum direction. So the displacement in the energy direction is inversion symmetry. It's strain, does not break time versus symmetry. This displacement does not break time versus symmetry. It's the displacement in the momentum direction which breaks time versus symmetry. And this spectrum, I mean, these are the typical things which people find in Arcus. And so presumably it exists, and the precise material origin for the mu term is, for the beta term, is something which I must confess my ignorance.
Maybe in continuation of the previous question, if you are an experimentalist and looking for these semimetals, which property of material can define these Weyl points and so on? I mean, the points in the group of the system.
Yes. So there exists now a complete. I mean, there are like 230 symmetry groups. There exists a complete classification of which have allowed for Weyl points, and basically the short thing is they're ubiquitous. They're everywhere. So it's not a question of, this is a big surprise. I mean, someone estimated that, I think there's this database of like probably 50,000 different materials, crystals, and that 10% of them support Weyl points. Now, many of these Weyl points are not useful because they're not at the Fermi level. Because this is completely different in graphene. In graphene, if you have graphene at half filling, you're absolutely certain that the Dirac points, the singularities, at the Fermi level. Here they can be anywhere. And so if they're far below the Fermi level, they're completely useless. So the struggle and the material science is not so much to find materials which have them, but to find materials which A, do not have too many of them, because that messes things up, and B, where hopefully they're close to trivial. So there's no symmetry principle governing them here. They can be anywhere, and you know, the field is making enormous advances. And I wouldn't say that the ideal system has yet appeared, but we're very close to it.
Yeah, it's not a question, a comment. There was a paper a while ago on a system with this geometry, a cylinder, and current proportional to magnetic field relation, similar to what you have, except that magnetic field was not imposed externally, it was a dynamical variable. A paper by Eliashberg, GTP letters, early 80s, and so
that's what you mean by while ago. Okay, I thought you said while ago.
Yeah, not that long ago, but some time ago. So what they showed is that in this geometry with a current proportional to magnetic field CME effect relationship, you get an instability in electromagnetic modes once your system reaches a certain length scale. This length scale, as far as I remember, was proportional to the inverse square root of your proportionality constant, J and B. Well, that's as much as I remember.
That's certainly something I should look into.
Yeah.
Thank you.
Okay, let's thank the speaker again.